Video 2, CL Prep. This one is just going to go through some examples now. So that's it. But first off, just for the examples, just to talk about how do you decide what to do on a problem. So here's some pointers that we're going to have, and we'll have more as we develop more tests and more ways to decide if things converge or not. So the things came to mind. At this point, if they ever actually ask you for the actual sum, the only way we know how to find it is it has to be geometric or telescoping. If, like the nth term test just tells you if something diverges, it doesn't have a sum. If you think of the integral test you can do, but it only tells you convergence. What you get for the integral is different from the sum of the series, because one is the whole area and the other is just adding up a bunch of points. So it's not going to tell you the sum. So that's kind of that's like a little hint here. If they ever say find the sum of the series, those are our options. Second, so if you're testing for convergence, first see if it's one you know or a variant on the one you know. Is it geometric? So check, see if it's geometric. Then it's very formulaic. We got a step-by-step way of doing it. Is it telescoping? You may need partial fractions. One that I was thinking I should put on here is it harmonic or a variation on the harmonic? That's when we know diverges. So those are options that we have. Then, if it's none of the patterns you know, make sure the terms approach zero, just informally. Just look and say, are the terms here getting closer and closer to zero? Otherwise, it just diverges. And then can you integrate if it converges, or if the terms approach zero, I should say, if the terms approach zero, then can you integrate what's left over? That'll tell you maybe we should do integral test. All right, let's look at the examples. So do they converge or diverge? And if they converge, can you find the sum? Here's the first one, sine of 1 to the n. So when you get a series problem in the beginning, one thing that can be kind of helpful is just to take a moment and write out what the series is, just so you can see the terms. So this is the sine of 1 to the 1 plus the sine of 1. It's always 1 to the 2. Remember, 1 is 1 radian, like around 57 degrees. So it's, I don't know, some decimal. Sine of 1 to the 3rd, and so on. Does this converge to a number? Now, we don't have that intuitive grasp we have over 1 plus 1/2 plus 1/4 plus 1/8, the geometric one. So we don't have that. So we just have to look at patterns and see what's going on here. And what I notice is that when I go to each term, it's just another power of sine 1 higher. This thing's geometric because I can just multiply each term by the sine of 1 to get the next term. If you have n in the exponent and nowhere else, that's kind of a sign that you're talking about something that's geometric there. And so this is an example of one that is. The sum is very clear. It's a1, so it converges because sine 1 is less than 1. It's some decimal between 0 and 1, right? And greater than 0. Just has to be between -1 and 1. So that needs to be true because the ratio needs to be between those numbers. Cool. And if it's geometric and it converges, you can find the sum. It's the first term over 1 minus r. So it's the first term over 1 minus the r. And that's the answer. That's what it converges to. That's it. We looked at this one in class. This is one that diverges by the nth term test because the terms aren't getting closer and closer to 0. Next one. I look at this one and I'm like, ugh. Okay, doesn't look geometric. I see n showing up a bunch of places and not in the exponent. I don't see any reason why it'd be telescoping or anything. What about the integral test? That looks something integratable. Let's think about this. So natural log of n is just a number. And notice I started at 2 because that way I avoided natural log of 1, which would put a 0 in the denominator. So it'll be natural log of 2, and then we'll have a 2 here, and then natural log of 3, and then we'll have a 3 there. That denominator is just getting bigger and bigger and bigger as n increases, which n is going to do. So this thing is definitely decreasing. There's no discontinuities in this function. Once you get 2 and greater, there's no discontinuities. And it's always positive. This is a guaranteed integral test. So instead of doing this one, So it's positive, decreasing, and continuous. So let's instead do the integral. Now notice I didn't say an equal sign because it's not equal to this. This sum is not equal to this sum, but the convergence is the same. So it's equal to the sum from 2 to infinity of 1 over n natural log of n to the third, dn. Maybe, I mean, I've never specified this, and this is not required. Maybe just to be clear, let's do x. Because now we're using x, and x is a number that can be anything. N we think of as 2, 3, 4, 5. And so now we just have to integrate this thing. Ooh, that's cubed. Can I make sure I can see that that's cubed? And so I got to integrate that. You could pause it, have a moment to practice your integration skills. Okay, what I notice is the derivative of natural log is 1 over x. So this is a chain rule situation. This is kind of a Lindstrom, but the derivative is already there. I've got a 1 over x that's there, and I've got a natural log of x to the negative 3 power, dx. I'm just rewriting it right now. Maybe I'll throw the limit in right now. This is the limit as b goes to infinity of the integral from 2 to b. Okay, so I just got to work out what this is. This is the derivative is present, so I'm good to go. Leave the inside alone and increase the exponent by 1. Put the reciprocal in front. Evaluated from 2 to b, limit as b goes to infinity. And so what is this? This is, let's plug in b. So it's negative 1/2 natural log of b to the negative 2 minus negative 1/2 natural log of 2 to the negative 2, limit as b goes to infinity. And put little brackets around it just to say that whole thing is getting the limit. And so, okay, b. So it's natural log of b to the negative 2, so it's in the denominator, and it's getting infinitely big in the denominator. That's negative 1/2 times a number really close to 0. That's 0 plus, minus minus. So 1 over 2 natural log of 2 squared. And that could be my answer. The book often will do a little like tricks here. They'll make it, they'll try to do some little like, cute algebra if they can with natural logs, but we'll just leave it like that. Okay, cool. So that one's done. Integral test. Oh, so I didn't finish it because this one, so it converges because it gets closer and closer to a number. So therefore this one converges. Yeah. And finally, last one, perfect, just checking time. Last one, we have this one. And you might recognize this as looking kind of like stuff that we saw before. And what we saw before is we saw the integral of 1 over x to the p, from 1 to infinity, dx. And this converged and diverged in very specific situations. Remember what those were? Okay, here's the idea. When the p was any number bigger than 1, it converged. When the p was 1 or less, it diverged. So if you have a bigger exponent down here, then this is getting smaller faster, and so it converges. So at the time, we called this a p integral, and it was just a little factoid we learned. Now, I'll let you know, most people don't talk about p integrals. That's not a thing. But what they do talk about is they talk about p series. And I was kind of setting you up for this moment right here. So a p series is a sum, this is a p series, is a sum of 1 over n to some power p, as n equals 1 to infinity, and it converges if p is greater than 1, and it diverges if p is less than or equal to 1. It's the same rule because you could just do the integral test on this and just say, oh, I'll just integrate it. Cool. So I integrate it, and when I integrate it, then it's going to tell me that it converges because I'm going to be in the same situation I was with the integral, right? With the integral. Okay? So you could say just p series with 1.04 is bigger than 1 converges. Boom. And you don't have to say any more work. We've got like two, well, we have two series that you just have kind of like, you can use this common language. We got the harmonic series, which is just the P series with P being equal to 1. And now we've got P series. And those are just know them, you know? Whoops, no. We're going to run into those a lot. But based on the integral test, that would definitely converge. And you can just say P series, and everyone will know what you're talking about. You don't have to justify it with the P series. There are more tests coming, but sorry, that's where we are now. Sorry for the fact that there's more. And what I want to do is I want to do a quick run through of, I didn't get to the right page. Hold on a second. Just a reminder that the textbook, if you go to the Larson Calculus textbook, you can get free worked out solutions that are totally available, especially to the odd problems. I don't know if it's to all the problems. I think it's just the odd ones. So if you want to see, get some help with the homework, you can always look here. Just wanted to remind people, because people were asking for help with the answers when they were working on these. Because these do get tough to recognize what the methods are. So at the end of the homework tonight, I think I assigned 71 to 78, pretty sure. And so I just want to give some ideas on this. So you've got some ideas on what you can do here. So let's run through, rather than run through the problems, let's run through the techniques. So first, can you see any that are geometric out of 71 to 78? Just those. And I gave you a hint before, when the end's in the exponent, that's a kind of a hint for it. So you can see this 2/3 to the end and go, ooh, yeah, that's going to be geometric. But then, this other one, that goes geometric too. Maybe write it down and think about it and see if that one's geometric also. Whoa, I'm going to have to do this fast. So what other kinds of things do we have? We've got telescoping. Kind of hard to see. Maybe this one's telescoping, but I don't know with that n squared and n cubed. Maybe I should write out a few terms and see if I get a better idea of what's going on with that one. Or maybe I want to integrate that, because those definitely are going to integrate pretty easily. And so maybe the integral test would be better on that one. We've got telescoping. We got that. We've got, you can see some of the examples I grabbed for class from here. We've got geometric. We've got integral test. So you can look at these and say, could I, like all the stuff in the denominators definitely get smaller. Could I integrate this? Could I integrate this? How about this? How about this? That'll give you some ideas. Hope this helps. I better stop before I run out of power. Good luck and take care, and we'll see you tomorrow.